Does anyone have a problem with understanding English? No? Okay, cool. So, just a little bit about myself. I'm Kenneth. I'm Microsoft MVP, and I work mostly in .NET and Azure. I'm Belgian. I live in Mallorca, and I work in London at a place called Epi Parking. So it's a small startup. And what we do is, as the name implies, we provide a parking app to people so they can find parking spaces and all that. And what we needed to do was digitalize all physical parking spaces in London and by extension in the UK. So we did that, and that's already a complicated task, but then, as we started growing, our CEO decided, parking is cool, but what if we map the entire world? I was like, cool, it's a very nice idea, but as you can imagine, the world and everything that's in there, it's not exactly that you can get it in a structured format and nice tabular data and then do queries on it. So the world is chaotic by its own nature. So the problem we faced is that all the data we got was in CSV files, plain text files, images, written text. So very chaotic and very heterogeneous data. And we had to import all of those into our database system. Now the problem is, before we can validate whether that data is correct, we have to import it. But once it's imported, well, it's there. So if it's then incorrect, so how do you then roll all of those changes back? And that's when we started building our system where we could roll things back. And it got very complex very quickly. So we decided, okay, how can we do this? And we're like, we use Git all the time for code, and that works really well. Just do things back, create a branch, throw the branch away, or merge it. So what if we use Git as a database? And at first we're like, yeah, that's not going to work, because Git's for code and it doesn't work. So we did a bit of a trial, and then we got to a point where we're like, oh, this actually works. It has some problems, but we can make it work. So I want to talk today a bit. I want to structure the talk in 3 parts. First, I want to look into the mechanics of Git as a database. So how does it work? Because we work with it through GitCrack and through SourceTree, through the Visual Studio client, or on the command line. But as a database, things are a little bit different. So I want to show you the internals of Git a bit, because we need those to use it as a database. And I'll talk a bit about why this is a really great idea and what the advantages are of using Git. And then I'll also talk about why it's really a bad idea and you probably shouldn't do that. Now, before I start, a few disclaimers. In this talk, when I talk about a database, I'm not necessarily talking about SQL or Oracle. So a database can be defined as anything where you can store data and get data back. So I'm going to use this term very liberally inside this talk. And the next term is NoSQL. And NoSQL is, for me, is a technical term, but it has become more of a marketing term as well, because everything is now NoSQL. Whenever it's not tabular, it's NoSQL. And in the context of this talk, I want to talk about NoSQL as being schemaless and non-relational. So how can we then use Git as a database? So we have the first way, where you can say, right, I'm going to create a new repository called a database. I'll create a JSON and store that into a JSON file, 1.json, add it to my staging area, and commit it. And then I can, get that JSON file back out. Cool, so I have a database. Well, that's if you consider the file system to be a database. There's a few problems with this. The first of it is, whenever you want to save something into your database, you first have to write it to the file system, and then do another operation to save it again in the file system. So that's really not a good way of doing things. The second thing is that you need your working copy. So as you know, Git has like the .git folder where it stores all the internal information, and then your working directory, which is just a convenience feature for you to be able to see a certain version of your files. So what if you want to see multiple versions at the same time in an application, for example? Well, then you'd have to create a working directory for each of those. And then obviously for each version you're going to have the whole thing duplicated everywhere, and that's going to cost a lot of disk space. So if we want to use Git as a database, we have to look at a bit how Git works internally. And Git has a specific data model, and I think most of you are probably familiar with this, where you have a bunch of commits that follow each other, so you have a history, and then you have branches which point at a commit. Now these commits, they don't really contain a lot of information. So a commit consists of the author, the date it was committed, and a message. That's at least the things we see visible inside, any of the Git clients, or when you do a Git log on the command line. But it has one more reference, and that's to a tree. And we can think of a tree as being a folder in the file system. So a tree consists either of blobs, which we can think of as files, or other trees that then can have more blobs, and you have a complete tree structure there. That's the internals of Git. And one distinction to make here is that Git actually consists of two databases. The first one is everything below the line, which is the object database. And everything in that object database is immutable. So if you write a blob, you'll never be able to change it. You can write a new one, but you cannot change the old blob. If you write a tree, you can never change it. And same with commits. If you've ever done a rebase in Git, you'll see that the Git hash changes, because if you do that, it just creates a new one, and it leaves the old one where it was. So you can never change anything here, just add. And then above the line, we have the branches, but also tags and other references. That's what they call the reference database. And those things can change, because obviously we can move master from the first commit to the second one to the third one. And branches in Git are nothing more than a simple text file. So you can look into the Git directory and you'll see your refs folder, and there it just says a file which is called master, which has the commit hash of this in it. So that's a reason why creating branches in Git is very easy, because it's only writing a hash to a file. And we tend to work only with commits and master. We don't really look at whatever is beneath there. And Git consists of two types of commands. We have the porcelain commands, which probably most of you are familiar with, even if you don't use them on the command line, but you use them through a Git tool. We're all familiar with pulling and pushing and merging and those things. Now these commands usually work on the basis that you have a working directory. So we can't really use these, and we need to use the plumbing commands. So all the porcelain commands use these commands underneath, and a lot of these, well, I looked them up, but I don't know any of those either. They do specific small little things, and then the other commands are composed of those. So if we want to use Git as a database, these are the commands we're going to have to use, because they deal with the individual items inside the Git databases. So how can we now build up our own graph of objects in that database? So let's start with blobs. So here again, I'm going to create a JSON document, simple ID and name, and then I pass it into git hash object. And that will return a hash of that file. Now the hash object, what it does is it takes that content and it creates a hash based on that content. So I can run that same command over and over, and it will always return the same hash. Whether it's on my PC or a different PC, it doesn't matter. So the arguments you see there, -w, that means that it has to write it through its database, and stdin just says that take it from the input there instead of from a file. So when I execute that command, I then have a blob, and I can read that blob back out by doing cat file and then passing in the hash, or the short hash, the beginning of that one, and it gives me back my document. So great. So now we have a key value store. I put in a value, it gives me back a key, and I can retrieve the blob by passing in that key. Now, as I said, the problem here is that as soon as I change that blob, well, then my key is going to change. So as a key value store, it's pretty lousy if we were only going to use this, because every time I change something, I have to remember to change the key as well. So we need to go one level up and go to trees. So to write a tree, you need to create a staging area, and you can think of it as the staging area you normally have when you have a working directory, but in this case it's going to be like a temporary staging area. So to create a staging area and add a tree, we call update index, which is a bit of a strange name for a command. It doesn't really say what it does, but there we can add a file and we pass in this reference of that blob and then a name 1.json. And then I can write that tree actually to disk, and that again gives me back a hash of that tree. And if I read that tree, I can see that it there has the hash of the blob, the name I want to give it to it, and what type it is. So now I can, through that tree, get to the blob. But still, I'd have to remember the tree, so we need to go yet another level up. And that's commit. Now I can echo out the commit message, pass that into git commit tree, and then pass in the hash of the tree here. So it will create a commit message, and again, give me back a hash. So everything is defined by hashes in Git. And then I can do a git log on that, and we see that we then have a commit which says like, right, 1.json was added, this is the author, that's the date. And now I can show my file based on that commit. So it will automatically see like, right, I have this commit and I'm looking for that name. So it will look up the tree, in the tree that name, and then go to the file and then show you the contents of that file. So now how do I update it? All the same thing again. I create a blob, I create a tree, and then I create a commit on top of that. And that commit, before we used to only do git commit tree and pass the hash in of the tree, but this time we pass in also its ancestor. So that's how Git can keep a history of all of your files by building the commits with ancestors. And now if I do a log on the last commit, I can see that it shows me 2 steps that happened to that file. So first added it and then made a change to it. And now again I can do that and I get the latest version of that file. But still, I need to remember, what is the last commit at this moment to get to my file. So the next thing comes on top, and that's references. So here I can say, okay, update the reference master and have it point at this commit. And then instead of remembering the last hash or the last tree or the last blob, I have a logical name where I can refer to and show the contents of that file. So that's all nice, but that's all shell commands, and we're really programmers, so if we want to use Git as a database, I don't really want to go to the shell and do all of these things. So what can we do about that? So there's a library called libgit2, which is essentially a C implementation of all the Git commands. So the API is a bit different, but it does everything that Git does, or almost everything actually. Right, but that's C. We want C#. So, or something else. I want C#, sorry. So there's a library called libgit sharp, and that's just a binding on top of libgit2, And for those of you who don't want C#, there is bindings on top of Ruby, on top of Java, on top of, you know, everything. So you can use all of these native methods directly through the language of your choice. So then how do we build a GitDB in C#? Well, first let's see what we need. What we need is a save method and a get method. We're talking about a key value store. You know, push in values, get back a key, then retrieve those values again by the key. So we need two methods: a save of t, where I pass in the branch the key and an object I want to store, and then I want to be able to retrieve that by passing in the branch and the key and getting back that value. So first thing we need to do is initialize a new repository. And in this case, I'm going to create a bare repository. And what's a bare repository? So normally if you have a Git repository on disk with code, you'll see that, you know, you have your folder with all of your files, and then you have the .git folder. A bare repository means that you don't have that folder with all of your files. You just have the .git folder where everything sits in there. So we don't have a working directory with a current version. So to do that in C#, you initialize a repository and then create a new instance of it. So let's suppose I have a current Git repository which looks like that. So how do I save a file in it then through C#? First we need to massage our value a bit into a stream, you know, by serializing it and then putting it into a memory stream. And then we can tell the object database to create a blob from that stream. So that will create a blob on disk and give us back a reference to that blob. Next part, we need to create a tree. So before I was just writing out trees because I was working on only one file, but you can imagine that this tree may have 500 files, and when I write a new commit, I don't exactly want to lose those 500. So what I need to do is copy that one. So the current, I take a look at the current commit, copy this tree, and into that tree I add this blob that I've created before. And now I can create that tree, which then points at that blob. Next part is obviously committing. So again, in the object database, I'm going to create a commit, where I pass in the alter and a message, a reference to the tree, and also a reference to the previous commit. And you'll see that it's a list of commits because one commit can actually have multiple parents in case you do merges or things like that. So then the commit is written to the object database, and the last part is updating the branch. So I get a reference to that branch name, and I just update it, and then the branch moves along. So by doing it like this, that allows me to work on multiple branches at the same time without having a complete working directory checked out. So I can store my files in different branches and do different things without having to store all my files. Obviously, only inside the Git directory they still will be there, but I don't have them duplicated. And then at the end I can return the SHA of the commit. So how do I now read that value back out? Well, we need to reverse the order. So we start on the master branch, get to the commit, get to the tree entry, get the blob. We read the text from there and then deserialize it again into an object of t and return that. So now I have my save and my get methods, and I can get all of that out. Right, but you know, I don't want to do that every time and for every application, so we've worked with this quite a bit at Happy Parking, and obviously I've now shown you the gist of it, but you know, there's no error handling, there's no synchronous asynchrony handling. There's a lot of more things and edge cases that you need to cover. And we decided to open source that, so if you want to have a look at the code and all the rest of it there, you can go to my GitHub repository. It's called Kenneth Truyers /gitdb, or you have the short URL beneath. And we've done a bunch of things there where you can access it over HTTP or locally, and there's a few things in there. So feel free to have a look. Now I must say this is still a proof of concept. We are using it in production, but we have our own we have our own set of problems there, and we've solved just ours. We're not ready to release this as like, hey, go ahead and use Git for everything. But you'll see these methods implemented probably in a slightly different way, but the gist is the same. Right, so now I want to switch gears a bit and talk about why this is really a good idea and what the advantages are. So first of all, and that's not specifically an advantage as Git, but it's an advantage of a key value store, is that it's schemaless, so you can easily move your application along, add fields to it, remove them, and Git won't really care. That doesn't mean that your data is schemaless or your application is schemaless. It just means that the data store is not going to enforce it. The same with non-relational. Using a non-relational database doesn't mean you don't have relations. It just means that your database doesn't really enforce them. So that allows you to move your code freely without having to worry about affecting your data store. Now another specific advantage for Git is versioning and rollback. That's quite obvious from Git. So if we get the current version of 1.json on the master, we can then update the master reference and then get back the previous version. And we can do rollbacks, roll forwards, and have a history of all the changes that were made over time, together with who made those changes, because all of your commits obviously also have an alter. And you can use Git tooling to look at all of this, so you could get a copy of that repository and do a git blame on any of your objects and see who changed it over time and when they did, and potentially also why they did it if they left a proper message. And related to that are obviously diffs. So if we do a diff between those two commits on the 1.json file, it tells me exactly what has changed. And I can do that between two adjacent commits or two commits that are half a year apart or are in different branches. I can do any diff there. So I can do that on a command line, but there's obviously plenty of tools available to do diffs as well. Now backups. So when you have a SQL database or whatever other database, you need to do backups. And usually when you do backups, well, you do them once a day, and then you keep the last 3 months, and then you save a copy every month or something like that, because you want to be able to roll back to a certain point in time. So how do you do a backup with Git? Well, you simply add a remote and then push your changes up to that remote. So Git is very good in determining what are the changes and only sending up the changes. And so we can use GitHub, but we can also use a different server. And then we can actually do replication as well. So how do we do replication? Git has the concept of hooks, which run every time you do a commit. So if you create a post commit hook and then push every time to your backup, that means that every change you make is going to be replicated to a different server. And you don't need this system of backups where you save a backup every time, because Git by default allows you to roll back to a previous state. And it's even better because it allows you to roll back to a consistent state, because you only have your commits as points in time where you can roll back to. So backup and replication is really easy. This is all you need actually. Then we have transactions. So you have transactions in SQL. We can do transactions as well, the short-lived ones, which are very similar to the ones we have in SQL. We can write multiple blobs to the system and then add all those blobs to a tree. And at this point we can decide to just do nothing, and nothing will be entered into the database. Or if everything is right, we can create a commit and change all of those files in one go to the system. And this command is atomic, so it either fails or it succeeds. So you can roll back a transaction very easily just by doing nothing, or committing it by creating a commit. So that's short-lived. That's very similar to what a SQL transaction is. Now what SQL doesn't have is long-lived transactions. So, and when I say long-lived, I mean a week, for example. So you want to make some changes in your system, but you only get the information on Wednesday, but you start on Monday with already preparing it, and you don't really want to go all of that to go live before you've actually done everything. So you create a new branch called transaction. On Monday you do a commit, on Wednesday you do a few others, and on Friday you finish it. Say like, right, this is good to go. Go back to a master branch and merge in that transaction. So that allows you to stage a bunch of changes, validate whether they're right, and then push them back in, or decide to just throw it away and delete the branch and get on with the rest. Right. So that's great. Let's all use Git as a database and throw away all of our old databases and use this. Not that easy, because there are a few issues with it as well. And we've run into all of these. For some we found solutions, for others we just live with it. So why is it a terrible idea? The first thing is also not specifically to Git as a NoSQL database. It's very common with key value stores. If you look at Azure table storage or blob storage, well, how do you query this? By key. You put in a value with a key and you get it out by that key. And that's it, except for a key prefix. And there is a disclaimer there, in that when you have trees, you can say like, right, for this tree give me all the blobs in that directory. And that will list you all those blobs, so that's nice, but it doesn't go recursively. So you can only go on one level with a key prefix. So what's the solution? We have our app talking to a Git database. So if we can't read from it, well then, why not just only write to it? And then for reading we use something else, such as SQL, Elasticsearch, Azure Search, Redis, whatever we can find where we have good query performance. We can do full text searches and all that. And that's really no different from other applications that work with a key value store. So this is what they would call CQRS in broad terms. And the problem with CQRS usually comes like, right, but what if we write? How do we then update or read store? And usually you do that by, whenever you write, you trigger some process that then denormalizes that data and pushes it to the read store. And Git gives us a little advantage there in that it has commit hooks. So whenever a commit occurs and we save something into that database, say like, right, something happened, we now need to persist those changes into our read store. And even better, with that commit hook, we also get a diff of the changes. So we know exactly like, here's the set of changes that just happened. So we know like, right, this file was deleted, this was added, this was updated. So now we can do in SQL, for example, create, update, and delete. Or in Elasticsearch or whatever we have. Next problem, concurrency. So the database usually will be accessed from different places. People will start storing data in there. And we're doing four things, essentially. We're creating blobs, creating trees, creating commits, and creating branches. So what happens if multiple people try to create a bunch of blobs? As I said before, the blobs are just a hash based on the content. So this case is actually fine. You can create thousands of blobs, doesn't matter. If people write the same blob, the worst thing that can happen is that you write the same file twice, but it's always going to work because you always have the same file. Then trees. Here we do have a problem. So say we have a commit history like this. So process A comes in and says like, right, I'm going to write a new file. So the first thing it does is copy this first tree here, which has a reference to blob A. So I copy it and I have a new tree that is the same as the previous one and points to that blob. I want to add a file to it, and now I'm going to commit. Now, before that commit happens, a new process comes in and says like, right, I want to add a file too. So it copies that first tree, adds a blob, and then starts to commit. And at this point you lose the second blob you have there. So that's an issue, and we need to protect against that. And we have the same issue when we go a level up on the commit. So process A comes in and says like, I want to create a commit with parent A. And then before I can update the branch, a new one comes in and says like, hey, I want to commit to, what's the current commit? And since master hasn't been updated, that still tells you that it's A. So C says like, right, my ancestor is A. And then when we move the branch, we lose the commit in between. So what's the solution here? Locking. So in C#, that's how you would do that. And sorry. So you only need to lock based on the branch. Whenever you're working on different branches, you can just go on, because those trees have nothing to do, because they will never be modified in different branches. So as long as you're working on different branches, you're actually fine. And then we have there a dictionary of all the branches, and we just lock whenever we start writing trees or updating commits and references. And performance, Git is not really web scale, as they call it. So I did a few benchmark tests on that, and I got to about 125 writes per second. So that means 125 commits per second. Now, on most of the applications that I've worked on in my career, this is actually sufficient. So 125 writes, it's not great, but I would say for 80–90% of the applications, and that's a number I invented, this is probably fine. But for the ones where it's not fine, it's usually not fine by a lot. So you have applications that do thousands and thousands of writes per second, so that would be a problem here. And it gets worse, because this was on a repository with 10,000 files. So what happens when we do it on a repository with 1 million files? That's worse. So now your 80% of applications becomes a lot less. Because most applications don't even do continuously 18 writes per second, but they might do in bursts. So sometimes you get a bunch of write requests, quickly put them in. So that's a bit problematic. So to see the solution, well, we first have to know, why does my write speed go down when I add more files? So let's suppose we have a tree with, a commit, a tree, and here we have 1 million files. I put 3 dots because 1 million files didn't really fit on the slide. So what if we now want to, if we look at the tree is just a text file which has 1 million entries. So that's a large file. So we want to add a blob to that tree. So how do we do that? Well, first we need to copy the tree and then add an entry for that blob. Now, if every time we do a write, we have to copy a tree of 1 million lines, then you can see that, where that 18 writes per second comes from. So storage now is quite fast, but still 1 million lines every second or every write is quite a bit to process. So there's various solutions here, or solutions or improvements, so to speak. The first thing is tree nesting. So before we had one tree with 1 million entries, and now we have different trees with each, like the top tree has 100 subtrees, each of those has 100 subtrees, and each of those has 100 blobs. So 100 times 100 times 100 is still 1 million blobs. It's just the structure that's different. And you can think of this as subdirectories. So instead of having one directory with 1 million files, you separate them out in smaller directories. So now what happens when I add a file? Now I only need to update this tree, and then the tree on top of that, and the tree on top of that. So instead of writing or copying one file of 1 million files, I'm now just copying 3 files of 100 lines. And that makes this quite a bit faster. So doing some tests on that with 1 million files as well, I got to about 250 writes per second, which is not bad. It's still not sufficient if you want to have like a high performance write application, but for most apps this is probably okay. Next solution, or next improvement, and this only works for certain apps, it's partitioning your data. So if we can have 250 writes per second per repository, if we make 3 repositories, or 5 or 10, we can multiply that read speed as long as you put them on different disks. And you can do that if your data is partitionable. And I'm talking about a situation where your company is active in various countries, for example, and you can just create one database per country, or a database per customer, or any other dimension you may have. And then the most promising solution, but the one where I had the least success with, is a different backend. So Git lives on the file system, and the file system is, or disks, or in generally not very fast. So libgit allows you to create different backends, and there's a few backends available. So we have Redis caches, Memcache, Elasticsearch, RavenDB. And so you can store all your blobs and your trees and commits and all that inside one of these. And that should theoretically be a lot faster than file systems. Now, I tried Elasticsearch and my write speed went down. Now the thing is, I tried this on a single node. So if you have a single Elasticsearch machine, well then all of that gets saved in RAM. So I haven't found out the reason for that, but I suppose that once you start scaling this up and you can put Elasticsearch over 5 different machines, then probably on a larger scale it will have some benefit. And there's other implementations there as well, and it's actually fairly simple to write one of these implementations because you just inherit a clause and implement some methods. Next problem, merge conflicts. So I'm sure that if you guys do a commit and a merge, it goes a bit like this, but the real world is a bit more like that. So what's the solution here? I don't know. We haven't found really what to do there. So one thing is, what we do currently is manual merges. So we have a whole bunch of people working on our data in parallel, different branches and all that. So we do manual merges, or we have a small UI written to resolve those things. We work mostly with geographical data, so you just put them side to side and tell the user, do this. There's different ways you can do this. And one of the good things is that in SQL you have the same problem. SQL just solves it by saying, last one wins, and just get rid of the old changes. At least here you have some options. You can do it in SQL, but you have to implement different patterns. But Git, from the start, tells you like, look, I have a merge conflict. What do you want to do with this? So you could say like, right, last one wins, same behavior as in SQL. Boom, overwrite it, merge conflict solved, everybody happy. But that's maybe not always what you want to do. So another possibility that you can do is like, right, I'm just going to commit this merge conflict. So I have my two JSON files, just on one line both, and I commit both of them to the repository. And then when you get that out, when you read, you actually ask the user, hey, which one's the right one? And he picks one, and that will be the next commit where that's resolved. So that's one thing you can do. We haven't done this because there's a bunch of problems involved in that if you then want to read without having it resolved before. So this is something we're still struggling with, but it's no worse actually than with other databases. Right, so to summarize, when do I think is it a good idea to use a Git database? It's mostly in applications that are very content heavy. So when I'm talking about content management systems, wikis, document databases, and the situation where we use it for is a content management system. I'm not talking about CMSs like WordPress, which would also be a good use case for this, but much more heavy content management systems as well, where you store geographical data and all of those things. And whenever your data is partitionable, when you can say, like, right, we're gonna make a repository per country, per customer, per whatever. Because then you kind of circumvent the limitation on the write speed. When do I think it's a bad idea? And small disclaimer, I think mostly it's a bad idea. So there's only like a few use cases where this is really a good solution. Bad idea is when you need fast writes, because of what I mentioned before, because you really can't do that. And when you need immediate consistency. So before, when I talked about queries, I talked about having the write side only write to Git, and then on the read side, read it from a different store. Now obviously there's a bit of a delay between that synchronization. So if you use Git and you want good query performance and performance queries, then you're gonna have to deal with eventual consistency. And that eventual consistency might be 1 second, or it might be 30 seconds or even more, depending on what you're trying to do. But you have to deal with it. Right, so then I want to show you a small demo of how this works in practice. I'm going to change over this for a moment. Yeah, it's fine. So I created a little application, and it's just a web API with a few REST methods where I can post some Google Maps pins. So you can see here I pass in the branch, a pin, and then I save it into the Git database. The same with the put, where I update one, I can delete one, and there's a method to get all of them. So this just uses the save and get from the Git database. And then at the bottom I have another method to get me the branches. So the application is really very simple. So here I have a map of Madrid, and I can start adding in pins. So let's add one. We're right over here, right? So I'm going to add in a few pins. There's that pin. Wait, what happened there? Right, so now I have a few pins, and I can now open Git Kraken and see that it has committed these things. And here I have used a repository with a working directory because I want to show this, but normally you wouldn't. But so we can see here that, you know, the 4 pins that I created are there in Git. And this gives us a few possibilities. I can see here that, you know, they're shown in the map. And I have this just auto-refreshing every few seconds to get the new pins or to get any changes. So what if I now go back to Git and say like, right, these last 2, they were actually wrong. So I'm going to reset this branch to this commit. Sorry. So now when this is reset, this then removes all of the pins that were there before. So I can roll forward, roll backward, and I didn't have to implement anything special. The only thing I had, the entire application, were those 4 action methods. So this comes out of the box. So the next thing I want to show then is if I create a branch from this. And I'm going to call this Retiro, for example. So this now shows me that branch in here because that also is in the update loop, so it just fetches the latest branches. And we see that we have the same pin that was there before. But now I'm going to go here, add in a new pin here. So I now have the 3 pins in the park there, but they all live on my branch. So I can switch back to master, and it takes a while. That's the application, that's not Git. Yeah, there you go. So that disappears. So that means that, you know, I can use this map to do all of my changes in a branch, and before they actually go live, I can have someone verify it. So get to the point where it says like, right, we want to, you know, work on a branch, but someone else is, you know, still on master, still doing some changes, and here say, this is the other park. So I have my 2 sets of changes now. On master I have this extra pin, and in Retiro I have these other pins, so I have 2 different working copies. So now, you know, someone comes in and says like, hey, that looks good. You know, I'm going to undo this. And I'm going to check out the master branch. And I'm going to merge Retiro into that one. So now if I go back, I switch to my master branch, I see that now the changes of those 2 branches were merged, and now I have all of the changes that were sitting there in a transaction, all of them together in my application. Now obviously someone did that, and then someone went like, oh, you know, we shouldn't have done that. So again, I can go back in there and say like, right, the master branch, really put it back to this. And then again, those changes are reverted, and I'm back to where I was. But then, you know, maybe some of the changes were right, but not all of them. So now I say like, look, that entrance pin, I still want that there. So I can right click here and say cherry pick. And that replays that commit on top of my master branch then. And I have my master with just that pin. So without using any logic, I've got all of this functionality for free with Git, because it allows me to do anything that I can do with a Git tool. I do this with Git Kraken or with whatever other tool. And then if we go a bit further, I've also attached this repository, which is on my local machine, and I've attached it to a GitHub repo. And now when I look here, it says created pin other park. I look at the commits, and I have the same commit that I have locally. Why? Because every time I commit, I do a push. So every time any change I make to the master branch is a push. And if everything is right, I should have also my other branch here, where I can see all of those commits as well. So without having to implement anything, I have a complete backup. I can move forward, move backward with all of this data. So that was my talk about Git. If you want to check out these sources, I've got the repository over there, all the C# code, so you can access it there. And if you want to read about all of this, I also wrote a blog post with a lot of this, but a bit more in-depth and a bit more theory about it. You can find my blog there, my Twitter handle, and I just want to say go ahead and use and abuse your tools, because this is really abuse of Git, because you might end up with something that is really useful for something that you would never imagine before. Thank you.